Welcome everyone. In this video, I will be covering section 16.8, Stokes Theorem. Stokes Theorem can be regarded as a higher dimensional version of Green's theorem. You already saw Green's theorem. Green's theorem relates to a double integral over a plane region D to a line integral around its plane boundary curve. So line integral over the boundary, which is oriented in the positive way, is equal to double integral over the plane region D that the boundary curve encloses. Stokes' theorem relates to surface integral over a surface to a line integral around the boundary curve of S. So Stokes' theorem connects surface integral to line integral. Green's theorem connects the line integral of the boundary to the double integral of the interior of D, for which the curve is the boundary curve. The following figure shows an oriented surface with a unit normal vector n. So we saw what a oriented surface was, non-orientable surface. The oriented surface will have a normal vector which decides the orientation. So upward upward normal denotes a positive orientation. Downward is the opposite of upward normal, which gives a negative orientation to the surface. S induces the positive orientation of the boundary curve C, shown in figure 1. It can be associated with the right hand thumb rule. What it means is if the thumb points to the direction of the unit normal vector n, then the direction the fingers curl is the positive direction of the curve C. This means that if you walk in the positive direction of C, with your head pointing in the direction of the unit normal vector n, then the surface will always be on your left. So you notice here you're walking along the boundary curve. You walk along this way and your head is pointing towards the unit normal vector, then that what it means is the surface is always on your left side. State Stokes theorem. Let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation. Let F be a vector field whose components have continuous partial derivatives on an open region R3 that contains S. Then integral over C, or integral over the boundary F dot dr, is double integral over S curl F dot D uppercase S, so vector. This also means we can say equivalently, we can say integral over C F dot T ds. D lowercase s represent the arc length, which is double integral over S curl F dot the unit normal vector to the surface followed by D uppercase. Yes, they are equivalent. We can see how they are equivalent. So we can say the left-hand side. How do we get this left-hand side? Integral over C F dot dr. We already saw this idea before. Just to recap this idea, integral over C F dot dr can be written as integral over C f of r of t, f of r of t. If we consider C to be a curve with a parametric representation r of t, then this can be written as dr is nothing but r prime t dt. In other words, it's integral over C f of r of t times, if I divide and multiply by length of r prime t, then I multiply by the length of r prime t dt. So this will be integral over C f of r of t, and this part is nothing but the unit tangent. So that can be written as dot t, t vector, unit tangent vector. And then we know that this part r prime t dt, absolute length of r prime t dt, is equivalent to writing the lowercase s, which is the arc length. So we actually proved that the left-hand side of this Stokes theorem, left-hand side of this Stokes theorem is actually equivalent to writing integral f dot t ds. We can write like this, integral over c f dot tangent ds. We can write like this, lowercase s here. Same way, the right hand side, if you notice, this is the left hand side of Stokes theorem. The right hand side Stokes theorem, which is double integral over s curl f dot ds, s uppercase, we can write that as, from what we did on the surface integral, it can be written as curl f dot, we know that surface area can be written as Ru cross Rv, provided you have the parametric representation of the surface. You can write like this. That is double integral over S curl F dot. Here also you multiply and divide by length of Ru cross Rv vector. Then you are multiplying again that by length of Ru cross Rv vector d uppercase S. Now this part is nothing but the unit normal vector. Saw that before. So it is double integral over S curl F dot N. And this part, what do you know about this part? This is nothing but the surface area, right? So this actually, here I have to make a minor change. This means it's du dv, which is same as ds. So it is going to be this will be dot n. This is the unit normal vector, and then the uppercase. Yes, we know that this part stands for the area of the surface, which is this part. And The normal vector to the surface is Ru cross Rv, unit normal vector. So it is length of that vector divided by the length of that vector. So that is how we do the right hand side. So finally we can say integral over C, line integral over the boundary curve of f is same as the surface integral of the curl f vector. So it is equivalent to writing like the second step that we have shown here. Stokes theorem says that the line integral around the boundary curve of S of the tangential component of f, because it's f dot t ds, t stands for the tangent. So we can say the line integral around the boundary curve of S of the tangential component of f is equal to the surface integral over S. It's equal to the surface integral over S of the normal component of the curl of F. The curl of F. So you might notice that there is a theme in Green's theorem and in Stokes theorem that we always see that integral over the boundary is integral over the inside. In the case of Green's theorem, it is line integral over the boundary curve is the double integral over the domain D that C encloses. Same way here, it's line integral over the boundary curve of the surface is the surface integral of curl F, which is inside the surface, that C is the boundary of. So similar idea is going on in both. And I have done problems 2, 3, and 10 in the videos for the section. Please refer to the videos for the sections. Videos for section 16.8 for problem number 2, 3, and 10. Yet the orientation plays an important role. If it's upward orientation, it is positive, then you have to change the sign if it is of different orientation, downward orientation. So please refer to these problems in the section videos. For this video, I will be doing this problem number 7. Use Stokes theorem to evaluate integral over C f dot dr. In each case, C is oriented counterclockwise as viewed from above. F of x, y, z equal to x plus y square I plus y plus z square j plus z plus x square k, and C is the triangle with the vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. So here we are going to use Stokes theorem to evaluate integral over C f dot dr. And you are given that C is oriented counterclockwise from viewed above. You are given F, and the curve C is a triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. Because the problem is telling us to use Stokes theorem to evaluate integral over C f dot dr, it's more like this. If you try to do the way the line integral part, it might be harder. So you have to use the positive orientation for this line join of 1, 0, 0 to 0, 1, 0, and then 0, 1, 0 to 0, 0, 1, and 0, 0, 1 to 1, 0, 0. So that part is harder. So whenever they say whenever the problem tells that you use Stokes theorem and evaluate one side of Stokes theorem, either the line integral or the surface integral part, which is the right hand side of it, so whichever they ask you to do, that part will be harder. So you may have to work on the right hand side. If they ask you for the right hand side, then you may have to look for the line integral. So in this problem, they ask you to do the left-hand side part of the Stokes theorem, which is line integral. So it is understood. It is it's a basic understanding here that definitely the right-hand side part is easier to evaluate. So we will try that. So first, we will recap what Stokes theorem is. So integral over C f dot dr is double integral over S curl f dot ds. And we know that this is what they ask. This is what you want to find. The reason being the right hand side may be easier to evaluate in this particular problem instead of doing the line integral. Sometimes a problem would be reworded as use Stokes theorem to evaluate double integral over S curl f dot ds, then that means that that side of Stokes theorem is difficult to evaluate, then you may have to work on the line integral part. So let's first find curl f. What is curl f? By definition, curl f stands for del cross f, which is a determinant I, J, K, and then dou by dou x, dou by dou y, dou by dou z. Then third row are the components of f, which is given in the problem, x plus y square, y plus z square, which is the y component, and z plus x square, which is the z component. So we will evaluate this curl f. So it is I times dou by dou y of z plus x square minus dou by dou z of x plus y square. Both seem 0. Then j times go from the right, dou by dou z of x plus y square minus dou by dou x of z plus x square, which does exist, the second part. Then k times dou by dou x of y plus z square, which is 0. Then dou by dou y of x plus y square, which does exist. So we notice here, this is 0, this is 0, because with respect to z, x and y are constants, and this part is going to be 0. Now this part does exist. We say, so j times 0 minus, so you get a minus 2x there, then plus k times, this part is going to be 0, and this has minus 2y. So we get this value to be equal to negative 2x, negative 2y. Let's see what we have written is right. With respect to y, so dou by dou y dou by dou y of z plus x square, dou by dou z of y plus z square. So made a mistake here, y plus z square. So that is not 0 then. It's going to be 2z. So it's going to be 2z with a negative sign. So you're going to have one more term here, negative 2xi. So its curl f is negative 2xi because this value is going to be 2z. So negative 2z I minus 2xj minus 2yk. All right, that is curl f minus 2zi minus 2xj minus 2yk. Now let's see what the surface is made of. Surface is bounded by the surface is bounded by the curve, which connects the points, which is a triangle actually, which connects the points 1 0 0 0 1 0 and 0 0 1. So obviously, if you make a rough sketch of this, it crosses x-axis at 1, y-axis at 1, and z-axis at 1. So the surface is actually a planar region bounded by, which is lying on the domain, which is lying on the xy plane, which is this part, the domain of this planar region this is mounted on, imagine that it is mounted on the triangle which is connecting the points 1 0 0 0 1 0. So on the xy plane, it is this part. So it's going to be a triangle with connecting 0 0 0 1 0 0 and 0 1 0. So it is two-dimensional, so we can consider that to be. So what is the equation of the surface? The equation of the surface is a plane. You know that it can be written as x over a plus y over b plus z over c equal to 1. Or it intersects the x-axis at 1 and y-axis at 1, z-axis at 1. So equation of the plane, equation of the surface or the plane here, plane is x plus y plus z equal to 1. And it is bounded by the curve C. Bounded by the positive oriented curve C, which is the boundary of the triangle. Bounded by the positively oriented curve C. Now this plane is over the domain. This plane lies over the domain D, which consists of the line joiner. If you consider the two-dimensional figure of the triangle below, x-axis and the y-axis, it cuts the x-axis at 1, y-axis at 1, so at 1, 0 and 0, 1. So this is our domain D. This is our domain D. So in order to find out the domain D, We have to find out the equation of this line join of A and B, which would be equation of line AB would be, you need the slope, which is difference in y over the corresponding difference in x, so it is -1. Then the equation would be y minus 0 equal to m times x minus 1. So y equal to -x plus 1. So the domain D, if you consider this part here, the domain D, and this part over here, they have the equation all those xy such that 0 less than or equal to x less than or equal to 1, and y actually runs from 0 less than or equal to y less than or equal to 1 minus x. So it is a line join from here to here. And this the equation of this line is y equal to 1 minus x. So it runs from y equal to 0 to y equal to 1 minus x. So that is the domain over which this planar plane lies, which is, and then C is given to be oriented counterclockwise. So we orient S upward. So we make sure all the requirements of Stokes theorem are satisfied here. Now, what is Z? The surface is given in this explicit form here. Surface is given in the explicit form, which means you can isolate the Z. Z equal to 1 minus x minus y. So Z is written as a function of x and y. That's why it is in explicit form. Why do we say this? Because we have to take the appropriate formula that we learned for surface integral. So we saw one formula for parametric, one formula for surface integral. So let's recap that idea that I mentioned earlier. So formulas for surface integral from 16.7, I just listed them for you. So the first one, double integral over s f dot ds is double integral over the domain, parametric domain, f dot ru cross rvda, where for a surface given in parametric form with the help of r of uv. But if has components pqr, then double integral over s f dot ds equal to double integral over d negative p dou g by dou x minus q dou g by dou y plus r dA for an explicit surface z equal to g of xy. So what are we evaluating here? We are evaluating the right-hand side part of uh, Stokes theorem. We are actually evaluating double integral over curl f dot ds, where the surface is defined, where the surface is given in explicit form. In the explicit form. So when we do a surface integral for a vector, we know that it has to go with the second formula that we wrote, because it's in this case it's explicit. So we have to go with negative p dou g by dou x minus q dou g by dou y plus r, where p and p, q, r are the components of the vector that you're choosing. Here, P, Q are the components of curl F. We already evaluated curl F in step 1. They have the components given by step 2. which is negative 2z, negative 2x, negative 2y. They are the components of curl F. So we said earlier, curl F equal to negative 2zi minus 2xj minus 2yk, which means P, Q, R of curl F is negative 2z, negative 2x, negative 2y. Now, in order to do this surface integral, we use negative P dou g by dou x minus Q dou g by dou y plus R dA, this will be dA, which is dy dx or dx dy, over the parametric domain, over the parametric domain. So what are we using here? This particular formula that we wrote here. So, so z is 1 minus x minus y. So dou z by dou x equal to negative 1. Dou z by dou y equal to negative 1 also. That is double integral over the domain. The domain is a triangle here, which where the domain runs from x value runs from 0 to 1, y value runs from 0 to 1 minus x. So the domain, we have the limits there. So we can take the limits 0 to 1, which are the definite limit for x, and y runs from 0 to 1 minus x. Then we are going to plug in these values here, negative 2z times dou g by dou x or dou z by dou x, they are the same, negative 1, and minus q, q is negative 2x, then dou z by dou y, that is also negative 1. So we got that. And then plus r, which is negative 2y. And then dA, which is dy dx. So it is integral 0 to 1, integral 0 to 1 minus x. So here it is positive to z, positive to z. Then we have negative 2x. We have negative 2x. Then we have minus 2y dy dx. But what do you know about z? Z is 1 minus x minus y. So minus 2x minus 2y all dy dx. So it is integral 0 to 1, integral 0 to 1 minus x. So if you distribute, 2x will get cancelled out. So you'll be left with just 2 dy dx. So minus p would become minus of minus 2z. So that will be a positive 2z. So it will become here negative 2z. So we have negative of that. So that's how we get that 2x and 2y get cancelled out. So you get a negative 2 dy dx. So negative 2 is after all a constant which can be taken out of the integrals. It is integral 0 to 1. Then you're going to integrate with respect to y. That will give us 1 minus x, then dx. So it will be negative 2 times x minus x squared over 2 between the limit 0 and 1. So it's negative 2 times 1 minus 1 half. That will be negative 2 times 1 half, which is equal to negative 1. So what we have shown in all of this, we actually took the right hand side of Stokes theorem, and we said double integral over S curl F dot ds equal to -1. Actually, what the problem is asking is the left-hand side of Stokes theorem. So we say integral over C F dot dr by Stokes theorem is double integral over S curl F dot ds, which we evaluated taking into account of all the requirements in Stokes theorem regarding positive orientation and all that. We got this value -1. Hope this video helps. As I said earlier, you can refer to the other problems, suggested problems, and the problems that I have done in the section videos. To problem number 2, 3, and 10, you can refer to the section videos for section 16.8. Hope this video helps.